Howdy folks, the day is finally here. We are going to talk about nicerarf and rmf files and talk about how to generate them. Roughly about 1 month ago, HEASoft version 6.29 released, and with that release came two new tools, nicerarf and nicerrmf, which could be used to generate ARF and RMF files to do spectrum analysis of nicer spectral data in xspec. And so we're going to talk about how to generate those files in this tutorial. Before we go any further, though, I need to preface that I am not affiliated with NASA, the Goddard Space Flight Center, HEASoft, or the NICER mission in any way. I am an independent researcher who takes advantage of the NICER mission and NICER data to facilitate my own research of neutron stars, pulsars, magnetars, and supernova remnants. So I will, of course, link all of the sources I'm using in the description down below. I will urge you to go ahead and check those out. And if anything I recommend differs from what any of the documentation says, I'll explain why, but note that you should proceed with caution when doing that. I would recommend following what NASA and the NICER team have recommended to do first before going out any further. Again, those links will be seen in the description down below. To be able to do any of this work, you're going to need HEASoft version 6.29. That is the version of HEASoft that has these two programs built in. Linked below will be this page in the NICER data analysis threads. These are for these explain NICER ARF and RMF files. I'll also be referencing the HEASoft ftools documentation pages. There are a few typos in these, and I will note them as I go through. But I personally like this documentation a little bit better, just because I'm used to more of like a GitHub style documentation or an API kind of documentation, and this is a little bit more of that. And the same goes for nicerrmf. All these three links will be linked down below, and I'll be referencing them throughout this video. Now, first things first is you're going to need a observation that has been processed with nicerl2. This has already been processed, and you can see I even have done a barycenter correction because most of my research work is actually timing work. But the first thing that we're going to need to do is we're going to need to extract a spectrum to work with, and this is the first point here. Per the NICER data analysis threads, you should not be extracting a spectrum or using anything spectrum related if you do a barycenter correction, which is something that I am guilty of doing in the past. I, again, mainly do timing work, so by default I always just barycenter correct everything I do, and I never really thought it had much of a effect on what I'm doing spectrum wise whenever I do some spectrum analysis on the few rare occasions that I actually do spectrum analysis. But you should use the non-barycenter corrected version if you are going to be doing any spectrum analysis. So what we're going to do is in this terminal window here, we're just going to open up xselect, and we're just going to read event. And we're going to read in our MPU7 cleaned event file right here. And that should work. Reset the mission to NICER. Okay, and now it's just as simple as typing in extract spectrum. And you can see all good counts. And then we're going to save spectrum. And we're going to just type this in, and then we can copy and paste the observation ID. What I always do is my default naming convention is just NI, the observation ID, and then obviously .pha to denote it as a spectrum file. And we should have that there. If we go back to our directory, there it is. There's our spectrum file. So we should be good to go. Exit. Don't save the session, doesn't matter. Okay. So now I'm going to pop this back open, and you can see here is our spectrum file, and this is going to be very important. We're going to start off with the nicerarf file, and so let's go look at that documentation. The nicerarf file calculates the effective area of nicer, and in order to do this, you're going to need a few different parameters. You're going to need the input file, which is going to be your spectrum file that we just generated, the rate ascension, the declination, the attitude file, otherwise known as just the filter file, the selection file, which can also just be the filter file if that's what you want. And what we're going to do is we're going to go through all the different use cases. So there are chapters in the description, and you can just click on which best suits you. But I'll recommend that you watch it all the way through, because knowing about all these is actually fairly important, depending on what it is that you're trying to do. Okay, so we're going to first start off with what I call the standard or the default way to generate an ARF file. Although this isn't going to be the most precise, I guess, ways of doing it, I recommend starting off with a default or a standard ARF file whenever you do spectrum analysis, and then you can kind of move into more of the precise or more selective ways of generating an ARF file that kind of have more of the bells and whistles on it. And so let's talk about this. So the first thing that we're going to do is we're going to just type in nicerarf, since that's going to be the command that we're going to be using. The next thing that we're going to put in here is just the path to our spectrum file. We're working in this directory, so we can just put the name of it. Now, the next two parameters that you're going to need are going to be the rate ascension and declination. Now, you could go ahead and look this up in the HEASoft archive, but then you're going to need to convert the coordinates to something numerical without the colons and things like that. And for this particular source, as you can see, this is for this XJ1808 low mass X-ray binary source. And so what we can do is we could just go over and use the HEASoft coordinate converter tool. You can see I've already have this typed in, and in J2000 coordinates here it gives us our rate ascension and our declination. So we can just copy and paste these right in wherever we need it. Separate them by a space. Okay, so we have the rate ascension and declination in already. Just quick recap: nicerarf, the spectrum file, or the path to the spectrum file if you're working in a different directory, the rate ascension, the declination, and then you're going to need the filter file. The filter file you can actually find in the auxil directory, or the auxiliary directory, and that is denoted with mkf. So we're just going to drag and drop that into there because that's a different path. And if you do that on Ubuntu, make sure that, any device really, or any operating system really, you should get rid of the single quotation marks on either side. Then what you should do is just copy and paste that one more time. Then you're just going to name the ARF file. And so what we're going to do is we're just going to copy and paste the name of our spectrum file. We're going to delete .pha, or just .pha, and then add in .arf. Okay, and one of the things that we're going to talk about in a moment is profiles. There are 4 different profiles that you can select depending on the source that you are looking at. So if we go into the HEASoft documentation, there are 4 different sources. There is point-like, a Gaussian surface brightness profile, a radial surface brightness profile, and a flat sky background. Now, if you do not set a profile, the profile will default to point, because NICER is a mission designed to look at neutron stars, which are oftentimes point sources. In fact, most things in the night sky are point sources, so it will default to a point source mode. So when we run this, we could really just type in profile equals point, but we don't really need to because it's redundant. It's going to default set to a point source anyways. So let that be known. We will talk about the Gaussian surface brightness, the radial surface brightness, and the flat sky background parameters in a moment. But for right now, at least for this ARF that I'm generating, you can go ahead and you can just hit enter, and it will begin to run. And this will take, I don't know, in my experience with the past few data sets I've done this with, it's taken about anywhere between 2 to 5 minutes. So it doesn't take terribly long, but it does take a moment, so just be patient and wait. Okay, so you can see the whole thing ran, and now it's done. And you can see now we have our generated ARF. You can generate multiple ARFs with this, but one of the things that you saw is you saw it go through all the different detectors, and those are the FPM modules, and you can actually turn off FPM modules. So what you can do is you can keep the same command as before, but you can type in the command detlist equals launch, and then a comma, and then you're going to select the different FPMs that you want, taken out, that you don't want involved, and you do that with a minus sign. So let's say we want to extract or ignore FPM 10, we can go minus 10, and then let's say we also want to do like minus 20. That will deselect FPMs 10 and 20. Now there is a little typo in this in the documentation here. Here is the command as it is shown in the examples. But you can see here for the 34, it does not have a negative. After doing a little bit of testing and looking at the nicer data analysis threads for the ARF and RMF files, which I highly recommend that you read through this. There's a lot of interesting information with regard to this. But with this, here you can see pretty much the same example, or a very similar example anyways, and you can see both of these are negative, and after doing some testing, both of them should be negative if you want them to be excluded. Okay. Now, I should also note that when you run this kind of a command, you should have done a little bit of filtering or deselection of those FPMs when you ran nicerl2. If you didn't do that, you may come into some problems, but that is a topic for an entirely different video. Now, additionally, you can go ahead and you can select which FPMs you want or that you don't want based off of a FITS file that you generate, ideally once you, select those FPMs when processing things through with nicerl2. And all that changes is you have this same command as before, but instead of the second filter file path, you would just type in the FPM selection .fits file, and I put 2 spaces there. That's not needed, but you would put in the FPM selection .fits file in that position, and then you would change the selection column, or you would type in cell call equals FPM in all caps underscore cell in all caps, and that would run based on all of this. Obviously, I'm not going to run it because I don't have an FPM selection. I didn't, select any specific FPMs. I used all of them. Okay, so now let's talk about the other 3 profiles that you can select. The first that we're going to discuss is the radial surface brightness profile. So to choose the radial profile, all you would do is just type in profile equals radial, and that's all you need to do. You don't need to mess around or change anything else. You just type in profile equals radial, at least in my testing, and it will begin to generate an ARF file based on this profile. Again, it's really important that you know what kind of source it is that you're looking at, because depending on what kind of source it is, you're going to want to mess with these different profiles. The next one is the Gaussian surface brightness profile, and so you could just type instead of radial Gaussian, and then you need one last parameter Per the documentation, you need this profile parameter, and that is going to determine the sigma of the Gaussian. So you can type in prof par, and then equals sigma colon, and then whatever you want the sigma to be. And that sigma is going to be in arc seconds. So if you want that sigma to be 10 arc seconds, you type in 10. If you want it to be 25, you type in 25. But that is going to be in arc seconds, and then you can just go about your business like that. So for the last profile is the flat profile. So you type in profile equals flat. And then this one has a different thing that you need to put in there also. That is going to be the angular unit, and you can see there's actually a wide variety of units that you can choose from. So you can go with an arc second, an arc minute, degrees, radians, or SR. Not exactly sure what SR is because I've never really used them, but you're going to need to type in one of these. So I feel like most people are probably going to want to use arc seconds. So you would type in ang unit equals arc sec, ang unit, and then whatever the name is, so ang unit equals arc sec, and then we could run that, and that would be generating an ARF based on the flat sky profile. Now again, you can generate multiple ARF files depending on what your needs are, but for me, I would recommend just going through and doing a default ARF file unless you've done something special or specific with your data reduction with nicerl2. Additionally, most of the sources that I look at are actually point-like sources, but again, it's important to maybe get a Chandra image or maybe a New Star image or an XMM image and get a look at the source that you are studying and pick the proper profile for that source. But as you can see, we already have our ARF generated, and we're going to use this ARF now to proceed. Now I'm going to show you how to generate the RMF file. So to do this, you're just going to type in nicerrmf. And just as a quick reminder, this documentation will be in the description down below. Again, I kind of prefer the HEASoft FTools documentation. And we're going to just go through these examples here. And so here's the first example. This is what I would call the default or standard way to generate a RMF file. So you're going to type in nicerrmf, and then you're going to type in the path to the spectrum file. Then you're going to need the filter file. Again, remember, you do not want these single quotation marks if you do the drag and drop method like I did. Then you're going to need to name the RMF, so we'll just do a little copy paste from before. Instead of ARF, we'll type in RMF. Then you're going to need det list equals launch, and then you're going to need to type in out mode equals RMF, and that way it knows to select all the detectors and then make sure that you're doing an RMF, because this can actually also create RSPs, which I've never really created RSPs before, but apparently they are sort of merged RMF and ARF files, so all you need is the RSP. I'm assuming RSP stands for response file, but anyways, so you have this is the default way, and I could hit enter and run this right now, but I'm not going to. And the reason why I'm not going to is because you really want to do this in a non-default way or a non-standard way. You want to generate an RMF based off of the weighting of the ARF. So let's do that method. And to do that method, things aren't really going to change too much, but you're going to need to type in a completely different command. So you only need to type in ls and then star.arf, and this is going to just select all the ARF files that are in here, and then a little arrow right here, and then we're just going to type in ni and then the observation ID, and this is the process of generating an ARF list. You don't really need to make the list if you just have one ARF like I have right here, but I think it's good to show this. And then we're going to go underscore ARF dot list. And just like that. And now if you go ls, now we have this ARF list file. And really that's just going to take, it's just going to create a list of the paths to all of the different ARF files. Okay, so now what we can do is we can go back and we can type in nicerrmf. You're going to need the spectrum file again. Just like before, you're going to need the filter file. You're going to name the RMF, and so we'll make that .rmf. Then instead of .list equals launch, you can type in .list equals at, and then you can copy and paste this ARF list. Now I should mention that if you just went through and did a default or a standard nicer L2 without messing about with the different FPMs, and you used .list equals launch, you can use .list equals launch again just to generate the default RMF. And then again, it's just out mode equals RMF, and RMF should be in all caps. I always forget about that. We can hit enter and just let it do its thing. Okay, so you can see here that we got an error right here, and the reason why we got this error is you generally speaking want this ARF .list, but that's really just going to depend on whether or not you selected different FPMs when processing your data with nicer L2 or reducing your data with nicer L2 rather, and then also if you didn't use .list equals launch with the ARF. So if you excluded certain FPM modules, then you're really going to want to create this ARF.list. But in reality, if you don't do that, you don't really need to do everything. So what we could do is we could actually go back here and then just change .list back equal to launch. Out mode equals RMF. Hit enter, and it will generate the RMF file for you. This will take a few moments, just like nicer ARF. This can take anywhere between 2 and 5 minutes in my experience in the dozen or so times I've done this. So again, this is new. This is a new feature, and I think a lot of people are still experimenting with it, as am I. But I've done it enough now where I feel like I could do at least a bare bones tutorial on it. Okay, so you can see that that is done, and if we look in the directory, now we have the ARF here, we have our spectrum file here, and then we have the RMF here, and we actually don't need this list file, so I'm going to remove that. Okay, so now you have everything that you need pretty much to do spectrum analysis in xspec, but there's one other thing that you could do. If you follow this here and make the ARF list just like you did before, you can type in everything just like before, but instead of naming the file as an RMF as we did before, you can type in .rsp and then change out mode to RSP, and it will create the RSP file. I've never used that before. Again, I do need to say, just so that everybody knows, I do mostly timing work, and when I do need to dive into some spectrum analysis, I'm not necessarily going too crazy with all the bells and whistles of everything. I'm just trying to get a rough idea of what's going on with the spectrum. Okay. So there's some other interesting things that can go on with generating these, but if you've worked with XMM Newton or Newstar or anything else, you're going to try, or you're probably going to want to try, to use group PHA to group these together, and that's actually not recommended in the documentation. I'll do a separate video on grouping these things together, but if you're going to want to do all of this in xspec right away, let's open up xspec. what you could do is you can just go and load everything in individually, and it should all work out perfectly fine. So you can go data 1.1 .pha, and it will load all of that in, and you can see it actually found the RMF file right away, which it's done that for me every single time. But you'll also need to load in the ARF, so you'll type in ARF, and then 1.1, and then the same thing .arf, and then your ARF is successfully loaded in. And you know, we can just take a look at this spectrum pretty quickly, and we'll ignore bad. So, we could go CPD XW and set plot energy, and you'll see you have this kind of weird, funky result. Generally speaking, from what I found in my spectrum analysis of at least SAXJ 1808 and also a handful of other sources, it's a good idea to try and ignore everything between 0.0 and 0.25 keV, and then we can just plot that again. And you can see now we have a little bit of a nicer spectrum here, and here you see actually something pretty cool with the this bump right here, which is believed to be hydrogen burning right here, and then helium burning right here, and then you have all the other cool stuff with this spectrum. But that's beyond the point. If you guys want to see a tutorial on spectrum modeling or spectrum analysis in xspec, I'll do that video for you. But that is more or less how you generate ARF and RMF files for Nicer. It's finally here. So many people are very excited. I'm very excited myself. Part of the reason why I've really mostly just done timing work is because I really like the Nicer mission. I really like doing things with the Nicer mission, but I didn't want to get too involved in doing spectrum analysis if I was just using the generic ARF and RMF files. But we have it now. It's all right here. Again, all the links to these three sites will be in the description down below. If you have any questions, feel free to ask away in the comment section, and I'll do my best to get to your question and answer it as best as I can in sort of a comment section kind of a format. If I get enough comments, maybe I'll do a follow-up video. Also, if I mentioned anything in this video while I'm editing it that is maybe wrong, I will correct myself in a pinned comment, so check the comment section for the pinned comment if I made any mistakes and I noticed them along the way. But I do want to thank you very much for watching, and I hope to speak to you next time, when maybe we'll do an xspec tutorial, or we'll do some other tutorial related to Nicer or HEASoft or something like that. But thank you very much again for watching, and I hope to see you again next time.